Some of the world's biggest challenges, they're really just giant engineering puzzles, and they can look impossible at first. But today, we're going to pull back the curtain on this brilliant strategy engineers use to crack these tough nuts. It's all about breaking them down into simple, easy pieces.
All right, so let's put ourselves in an engineer's shoes. Here's our puzzle. We've got this block of a solid chemical. It's called phenol. And our job? We need to figure out exactly how much energy it's going to take to turn it from that solid all the way into a superheated vapor at a totally different temperature and pressure. Yeah, I know, it sounds super specific, right? But this is the kind of problem engineers have to solve all the time.
Okay, but here's the kicker. You can't just Google this. There's no big table of answers or a website you can just plug the numbers into. No single neat little formula exists for this exact transformation. So, what do? How on earth do you solve it? Well, this is where the real magic of engineering problem-solving kicks in.
They use something we can call the secret path method. See, instead of trying to solve that messy, direct jump from A to B, they find this incredibly clever workaround. The big insight here is that you don't actually have to figure out the hard path, because the answer you're looking for doesn't depend on it. And it all comes down to one really fundamental concept. And that concept is called a state property. Now, the idea here is actually pretty simple. It just means that for certain things we measure, the journey you take to get there, it just doesn't matter. All that matters is where you start and where you finish. Let me give you a really simple way to think about it. Okay, imagine you're driving from the bottom of a mountain to the peak. The total miles on your car's odometer? That definitely depends on which road you take, right? The long, winding one versus the steep, direct one? That's path dependent. But what about your change in elevation? The actual difference in height between the bottom and the top? That's a state property. It doesn't matter if you took the scenic route or a helicopter straight up. The change in altitude is exactly the same.
And this is the breakthrough moment. The total energy change we're looking for, engineers have a fancy word for it, enthalpy. It's a state property. It's just like the elevation on that mountain. And if the path doesn't matter, well then we can just completely ignore that complicated, messy, direct route. We can literally invent our own path. A totally made-up, hypothetical path made of super simple, easy-to-calculate steps as long as it starts and ends in the exact same places.
So, what are these simple steps? What does our made-up path look like? Well, it's really built from just two basic building blocks. The first one is pretty straightforward. It's the energy you need to just change the temperature of something without changing what it is. Just heating up a solid or a liquid or a gas.
This is called sensible heat. And that's a great name for it because it's the heat you can actually sense with a thermometer. You heat a pot of water, you watch the temperature climb, that's you adding sensible heat. It's super predictable, and engineers have this down to a science.
And this is why engineers love this step. The math is easy. It really just depends on three things: how much stuff you have, how much you're changing the temperature, and this known property called specific heat capacity. All of those are things you can look up or measure easily. So, boom, puzzle piece number one is sorted.
All right, on to our second building block. And listen, this one is often the real energy hog of the whole process. We're talking about changing phase. The energy it takes to melt a solid into a liquid or boil a liquid into a gas. This is called latent heat. Latent literally means hidden, and that is the perfect word for it. Think about boiling water. The temperature hits 100 degrees Celsius, and then it just stops. It stays there, even though you're still blasting it with heat. So where is all that energy going? It's not raising the temperature anymore. It's doing the hidden work of ripping the water molecules apart from each other to become steam.
And the amount of energy we're talking about here is just staggering. Seriously, if you look at water, the energy it takes to heat it all the way from freezing to boiling, that's the sensible heat, it's nothing. It's tiny compared to the absolutely enormous amount of latent heat you need to actually turn that boiling water into steam. Phase changes are a massive, massive energy investment.
Okay, so we've got our two tools, our two building blocks: sensible heat for changing temperature and latent heat for changing phase. We're ready. Let's go back and finally solve that phenol puzzle. So instead of that one impossible jump, here's our simple step-by-step recipe. First, we calculate the sensible heat to warm up the solid phenol right to its melting point. Step 2, we add the latent heat to actually melt it. Step 3, we add more sensible heat to warm up that new liquid until it's ready to boil. Step 4, we hit it with a big dose of latent heat to turn it all into vapor. And then finally, Step 5, one last bit of sensible heat to get that vapor up to our final target temperature. See, each little step is a simple, known calculation.
And here's the best part. The grand finale. All we have to do is add up the energy from each of those 5 easy steps. That's it. And because the total energy change is a state property, the final number we get from our simple made-up path is the exact same answer we would have gotten from the super complicated direct path. It's the right answer, problem solved.
And you have to understand, this isn't just some clever one-off trick. This whole divide and conquer strategy, it is the absolute backbone of chemical and process engineering. It's how they design systems for, well, everything. From refining oil and making life-saving drugs to figuring out exactly how much steam you need to power an entire city. It's the key to turning these seemingly impossible problems into a simple to-do list.
The source material for today's explainer comes from Dr. Bagazadeh, who really sums it all up with this great advice. Stay curious, keep learning. And that's exactly it, right? It's that curiosity that lets engineers come up with these beautiful, elegant solutions, like the hypothetical path.
You know, when you really think about it, this is so much more than just an engineering lesson. It's a powerful way to think about any problem. It shows us that if the direct path to something you want seems completely impossible, maybe you just need to step back. Find the one thing that doesn't change no matter what route you take, and then invent your own simpler path to get there. So my question for you is, what complex problem in your life could you solve by thinking about it that way?